Hey everyone, Mr. Fransky here. Today we're going to be talking about just some integration by parts practice problems. This is just going to be straight up integration by parts, none of the fancy cyclic or table method as are in other videos. But here we're just going to talk about kind of attacking a problem, seeing why you have to use integration by parts, and then going for it. So let's take a look at some of the vocab we're going to talk about. Indefinite integral, that's the stuff we've been talking about lots. Antiderivatives, of course, that's what indefinite integrals are all about. Integration by parts is what we're focused on here, and then how to find u, du, v, and dv. Those are kind of the important parts that we use in integration by parts. Alright, so we've seen this before. This is our formula for integration by parts. Integral u dv is uv minus integral v du. We proved that using the product rule, right? This is just kind of a rewriting of product rule. And then we talked about how to choose u, right? These are good choices for u. So the choice in order for u. So you want to use logs, inverse trig, polynomials, exponentials, and then trig. And I'm going to go through kind of problems for the first three here, and then I'm going to talk a little bit about the last two and how they aren't used really very often. So first we're going to take a look at some with logs. So these are kind of just four different problems, types of problems that you might be given, and some of them use u substitution, some of them use integration by parts, and we're just going to kind of talk through each one. So the first one I just have natural log x. So if I try to think, is there any kind of choice for a u substitution here? Well, I don't really have many choices, right? U equals x is never a good choice for u substitution, and if u is natural log x, then my du would be 1 over x, which I don't have. So u substitution is not going to work here. So now I kind of jump ship and I try integration by parts. So think about limit. So I'm going to make u equal to natural log x. That means dv is everything else. Well, everything else in this case is just dx. So we may not have seen that before, but in this case, it's not too bad. It's just going to make my dv very simple, actually. So if u is natural log x, then du is 1 over x dx. And if dv is dx, if we integrate both sides of this, we're just going to have v is equal to x, right? Because there's technically a 1 dx here, and so if we take the derivative of both sides, dv dx would be 1, dx comes over. So now we have all our parts, so we just put it in. So we do uv x ln x. So uv actually did vu because I didn't want to write ln x and then x after it, minus integral v du. So that is x times 1 over x dx. Hey, that's really nice. What's x times 1 over x? I think that's just 1. So I have x ln x minus just integral of 1 dx. So I'm just going to write that as integral dx. Integral dx, the antiderivative of 1 is x. So this is x ln x minus x, and then don't forget your plus c. This is actually one of our big 15 integrals on the back of your sheet. And this is a good one to know, but if you don't know it, you can do integration by parts pretty quickly to be able to figure out what this is going to be. All right, the next one we have x or ln x over x. So you may have noticed when I talked about u sub, if u is ln x, in this case du is just going to be 1 over x dx. We have that. So in this one, it looks like we might actually be able to use u sub. So always check to see if you can use u sub first. So if I do this substitution, I would then have the integral. So ln x is u, and then 1 over x dx is just my du. So it's just u du. So antiderivative of this is u squared over 2 plus c. And now I plug my u back in. So this is natural log of x squared. I'll put it like this. You could do natural log squared x, kind of like sine and cosine, but I prefer to do it this way. And that's divided by 2 plus c. And you can check your work. If you take the derivative, the 2 would come to the front. It would cancel with the 2 on the bottom. And then we multiply by the derivative of the baby function, which is 1 over x. We would have natural log x over x, and that's exactly what we need. Not bad. All right, the next one, if we try to do this same u substitution, the problem is I have another 1 over x hanging out, right? So I would have u, but I would still have a 1 over x multiplied, and so I don't want that extra x in there. So in this case, I think we're actually going to have to use integration by parts. So what I'm saying here is that if you did the same substitution, you would have u for ln x, then you would have times your du is the 1 over x dx, but you would still have a 1 over x hanging out. And if you try to solve this guy for u, you would have, or x, excuse me, you would have e to the u power. So back substitution isn't going to work great because I would have an e to the u on the bottom here and still have a u on the top. Everything points to having to use integration by parts on this one. So now let's try it. So I'm going to think about limit. So good choice for u. Log is number 1. So let's do ln x. So then du is 1 over x dx. And dv then is everything else. So let's see. So u is ln x, so then everything else is 1 over x squared dx. That is x to the negative 2. Antiderivative of x to the negative 2, we add 1 and divide by the same. So v would be x to the negative 1 over negative 1. Or we could write that a little bit better. That would just be negative 1 over x. All right, now let's put our pieces together. So uv uv is going to be natural log x times negative 1 over x. That's negative natural log x over x minus the integral of v du. So that's negative 1 over x times 1 over x again, dx. Okay, so that's negative ln x over x. And then these two negatives are going to cancel out to make positives. Let's put those in. And then we have 1 over x squared. We just did that antiderivative right up here. So this is plus the integral of x to the negative 2 dx. So that's going to give me negative ln x over x. Like I said, we just did this, right? This is going to be minus 1 over x and then plus c. There we go. Okay. This is the next one over here. We have, keep jumping on me. So we have x squared ln 4x dx. So we've seen some with this x in the front, but often we have trig or an exponential over here. This time, be very careful about your choice of u. We want to use it in the order that we have with lipit, right? So we're going to use log. So I'm going to use ln of 4x. And then my du is going to be, this would be 4 times 1 over 4x, right? Because I have to chain. The 4's actually end up canceling. So my du is still just 1 over x dx. And then my dv would be, in this case, x squared dx. That means that my v would be x cubed over 3, and that's it. Okay. All right, so I'm going to put it together. uv, so I have, let's write this as, let's see, x cubed ln of 4x divided by 3 minus the integral of v du. So v du, let's see, is going to be x cubed over 3 multiplied by 1 over x dx. That's nice. One of those x's cancels. So we have x cubed ln of 4x divided by 3. It's not a grade 3 up there. Let's fix that. And then minus the integral. Let's see, I can pull out a 1/3. And x cubed over x, that's just an x squared dx. So antiderivative of x squared is x cubed over 3. Let's see if we can do this in one step, because I'm running out of space. So we have x cubed ln of 4x over 3 minus, let's see, we'd have 1/3 here, we'd have x cubed over 3 here, so it looks like we would have x cubed over 9 altogether plus c. That's where I'd stop. Cool. So 4 ways to do log problems. 3 of them needed integration by parts. This one right over here, we actually were able to do just using u substitution. All right, let's try another problem. So now we're going to deal with some inverse trig functions. So most useful thing for using parts in this is just doing the straight inverse trig function. This is going to be similar to when we did just natural log. We're going to use u as just our inverse trig, and then our dv is just going to be dx. So in this case, once again, you try to think about u substitution. There's really no choice, right? Because if you do u as arc sine or sine inverse, right, that's the same thing. Then your du would have a 1 over square root 1 minus x squared, which is not here. Same with tangent, right? I don't have the derivative as part of my integrand. So in this case, what I'm going to do is I'm just going to say u is sine inverse x. I'm going to do sine inverse instead of arc sine. It means the same thing, though. So then du is going to be 1 over the square root of 1 minus x squared dx. dv is whatever's left over after the u, so that's just dx. Now remember, that means that v is equal to x, right? Because you're integrating both sides. Integrating dv is v, integrating dx is x. Or you can just think the derivative of x is 1. Okay, so let's put the pieces together. uv, so we have x sine inverse x minus integral v du. That's going to be x over square root 1 minus x squared. Ah, this looks like something we can use u sub on. Yep, so it looks like if we make u, and maybe better to use a different letter. I'm going to use u anyway because it's u sub. So just forget about these u's up here. We have a new u now. So u is going to be 1 minus x squared. So then du is negative 2x dx. So I'm going to put a negative 2 up here to make this work out. So negative 2 goes up top. And then I have to put a negative 1/2 in the front. Cancel it out. So we now have x sine inverse x plus 1/2 integral. So let's see here. The negative 2x dx creates my du. And then I just have u to the negative 1/2 du. So that is x sine inverse x plus 1/2. Now if we add 1 to negative 1/2, we have u to the positive 1/2 divided by 1/2, and then plus c. So that is x sine inverse x. So the 1/2s here actually cancel. right? You could think about it multiplying by 2 as well, but not too bad. So then u is 1 minus x squared to the 1/2, so that's going to be plus square root of 1 minus x squared plus c. There we go. A little bit messy for a derivative of an an inverse trig function, but antiderivative of an inverse trig function, but really not too bad with the math doing integration by parts here. Last one, we're going to do the same method. So u is going to be tan inverse of x. That means du is 1 over 1 plus x squared. So dv is dx. That means v is equal to x. So uv, x tan inverse x, minus the integral of v du, which is x times 1 over 1 plus x squared dx. So again, if I do u substitution here, let's do u is 1 plus x squared, then du is going to be 2x dx. So I need a 2. That means I need a 1/2 out front. So let's see here. We got x tan inverse x minus 1/2 integral. So let's see. The 2x dx turns into my du, which is going to be 1 over u du. Okay, so antiderivative of 1 over u is going to be natural log. So we have x tan inverse of x minus 1/2 ln absolute u plus c. And u is 1 plus x squared. That is always positive, so I don't need the absolute values. So we have x tan inverse of x minus 1/2 ln of 1 plus x squared plus c. There it is. Okay. So we've done L and I right now. We did logs, we did inverse trig. Let's try one with polynomials. So these are more like the ones we've done in class already, but let's do them anyway. So in this first case, my best choice for u is going to be the polynomial here because I don't want it to be trig. So if u is 3t plus 5, then du is 3 dx. And then my dv is everything else, so it's cosine of t over 4 dt. Integrate both sides there. We have v is equal to antiderivative of cosine of t over 4. It's going to be something about sine of t over 4. Then think, if we took the derivative of this, I would have a 1/4 out there. So to cancel that out, I need a 4. Now I put it together. uv, 3t plus 5 times 4 sine of t over 4 minus the integral of v du. So all together looks like we're going to have 12 sine of t over 4. dt, it should be a dt, not a dx. Okay, we'll pull that 12 out, so we have 3, let's pull that 4 to the front, I guess, maybe as well. You could distribute it, I'm actually going to leave it where it is, because you can have it wherever you want. 3t plus 5 times 4 sine of t over 4 minus 12. Antiderivative of sine of t over 4, we kind of already did it up here. That would be negative 4 cosine of t over 4 plus c. Okay, so we can circle that and be done, or we can make it a little prettier, right? So maybe we distribute this 4, I don't know, sure. 12t plus 20, since I can't decide whether or not to do it. Sine of t over 4. Negative 12 times negative 4 is a positive 48 cosine t over 4 plus c. There we go. All right, this next one we have a definite integral. Okay, I'm going to talk about what a definite integral looks like in this case. Really, it just works the same as we did before. We find the antiderivative, so we get all the way to here, and then we're going to evaluate it from -1 to 2. The only thing that's going to be different is the c won't really matter. So let's give it a shot. So x e to the 6x, I'm going to use u as x. Then dv, well, let's do du first. So du then is just dx. And then dv would be e to the 6x dx. Integrate both sides. So v then, this is the derivative of e to the 6x, right? We leave that alone. But then we'd have to chain by multiplying by 6, so I need a 1/6 out front to cancel out that 6 when it chains. Okay, let's put it together. So we have uv, so I have x over 6 e to the 6x minus integral v du. That's 1/6, I'm going to pull that 1/6 out. E to the 6x dx. And we're integrating this from -1 to 2. So often what you'll see is they put this in here, and they'll also just put it here like you evaluate it, -1 to 2. Don't have to worry about changing any limits when we do integration by parts, because we're just using this to find the antiderivative, then we'll plug it in. So that is x over 6 e to the 6x, evaluated from negative 1 to 2, minus 1/6 times, this is going to once again be 1/6 e to the 6x, evaluated from negative 1 to 2. Now plug things in. So we plug the 2 in here, we have 2/6 e to the 12th minus negative 1/6 e to the negative 6. That's our first part. Minus 1/6 times 1/6 e to the 12th minus 1/6 e to the negative 12th. Negative 6, excuse me. Nope, because I don't want to do the algebra, I'm going to circle that, right? You could combine maybe some of these e to the 12th, some of these e to the negative 6, but that's all we have to do. Okay, so notice there was no plus c anywhere in here. All we had to do was plug in the 2 and the negative 1 to our antiderivative. Awesome. So, on the last slide here, I'm just going to kind of talk about some of these other things. So, if you have an annoying polynomial like x to the 5th, remember if you do the integration by parts on this, you're going to have a 5x to the 4th and then like a 1/2 e to the 2x in your integration part when you do integration by parts. And so you're going to have to do parts again. You're going to have to get this 4 whittled down to a 3, a 2, a 1, a 0. So if you see something like this, I'm going to encourage you guys to watch the video I have on the table method, and you're going to use that. Because it's going to be a lot faster than having to do integration by parts 5 times. So you're going to tear your hair out. The exponential and trig, if you have them together and you have no other option, you have to make one of them u. Usually I choose u to be e to the x, but it's about the same each way. If you do e to the 2x in this case. If you do the exponential or you do the trig, it's going to be pretty equally terrible. But if you watch my video about cyclic method for integration by parts, it makes this a little bit easier. You only have to do integration by parts 2 times, and then you end up being able to solve for the integral using a little bit different technique. So be sure to watch those videos if you need them. Otherwise, I hope you were able to get some integration by parts down, and I love you guys. That's why I'm here. Have a great day.